In a sequence of positive integers, each term after the second is the product of the previous two terms. The sixth term is 4,000. What is the first term? So let's say we have A, B, C, D, E, 4,000. Okay. In a sequence, each term after the second is the product of the previous two terms. Okay. So 4,000 DE is equal to 4,000. And then it's true that, let's think here. E is equal to C times D. Okay. So A is equal to, from this, B over C. Let's see if we can maneuver some things around. We can get BC in there. So from there, BCE is equal to 4,000. Yeah, thinking about this. Let me see if I notice a pattern with this. So, we could think about this as factors of 4,000. So 4,000, if we break it down into its prime factorization, and that's just 5 to the third. So 4,000 is equal to, how many twos? 2 to the fifth times 5 to the third. So it's got to be true that D times E is equal to 2 to the fifth times 5 to the third. And E is obviously bigger than D. So, I mean, what if we just simply said, Now, it wouldn't quite work if e was just 5 to the third, because then d would be 32. 32 times something doesn't equal that. E could be, it's got to be 5 times something. So E could be 5. What if E were 5 squared times, or 5 to the third times 2? That would be 250. 250, 4,000. And what times 250 is 4,000? 250 times 16. Then if we just had no. Thinking through here. Definitely not doing this in the most efficient way. 8 2. The thing is that 8 times 16 is not 250. Thinking about this in a smarter way. Okay, DE is equal to 2 to the 5th times 5 to the 3rd. 8 times 16, yeah, not. I mean, what if we didn't use all the 5s? We just did E was equal to 5 squared times maybe 2 to the 3rd. So that's 25 times 8 is 200. 4,000, 200, and 200 times what? So 200 times 20 be that. Yeah, 5 to the 3rd. Yeah, so we'd have 5 squared times 5 squared times 2 to the 3rd. Then we'd have a 5 times 2 squared. Yeah, then we could have 20. That works. Then what times what can give us 20? Well, 20 times 10. And then, yeah, no, because then it's tricky. Yeah, then we run into issues here. So we see it's not going to work. Like if I have a 2 here, then this, Yeah, that doesn't work. It's just different iterations of this. So 200, that was the 5 squared times 2 to the third. What if we try 5 squared times 2 to the fourth here? Then this number has to be 25 times 16, which is 400. So we could have 4,400. This would then be 10. And 10, yeah, the bigger it gets, interestingly, the tougher it is to do. So this 250, we're back here. This was the 5 to the third times 2, which didn't work as well. Let me see, did it work? And then we do, yeah, 250 times 16. Yeah, then we'd have to do 16 times what gives us, I don't know if, yeah, prematurely doing 8 there. 16 times what gives us 250? Times 10 is 160. Yeah, this is 2 to the fourth. 2 to the fourth. Yeah, I think we want more 2's in this. Like if we go 5 squared times 2 squared, that is 25 times 4, which is 100. So if we have 4,100, this could be 40. And then 40 times what is 100? Yeah, then that's tricky. That doesn't work. Make sure reading. So each term after the second is the product of the previous 2 terms. Sixth term is 4,000. So 100 won't work. What if we just did 5 times 2 to the third, which is 5 times 8, which is 40. Yeah, but then it's not big enough. Then this would have to be bigger. 5 times 2 to the fifth would be 32 times 5. Yeah, interesting. Is this 16? Yeah. I multiplied this right. Yeah, 1, 2, 3, 4, 5. Okay. 2 squared times 5 squared. 5 times, so 25 times 8. Yeah, we've tried the 200 though. Didn't work. Unless that doesn't really matter because there's no previous term before this. So this could be it. And it works. and it's not a big deal because there aren't two terms before this 2. So actually, I'm going to say the first term is 5. So choice D.